for today is just to discuss an example of a two-shifted symplectic structure and also of the two-shifted Lagrangians that are associated with it. So the basic object for us is going to be a Lie group equipped with a metric, which is ad invariant on its Lie algebra. Okay. Okay, so
should we think it's real or complex, or it doesn't matter?
It doesn't matter. Let's say it is real.
Okay.
So let's recall the Balt-Schulman complex of Lie group. Okay. Here we have the RAM degree. You have the simplicial degree. So we're talking about two forms. You have 0, 1, 2. We only care about what happens on this part of the diagram. And since we're talking about shift 2, we're considering a two form that lives on simplicial degree 2. Right? So here we have here we have 0, right? The base R. Okay. So the two-shifted symplectic structure that we care about lives here. Okay.
I'm sure the bottom row is correct. Is the bottom row correct? It's R00, right? Because it's just a point, and we're taking two forms on a point.
Yeah.
So it should be 0.
Yeah.
So it's because G, it's a group over a point. Right? It's just a group. So because it's a point, it's just R00.
So this two form has this expression. Okay. D denotes the simplicial phase map. It's given like this. Okay. So this thing lives here. And the three form associated with this is the Cartan 3 form. Okay, minus. So I think that in this form, this structure first appeared on.
So wait. So I know it's annoying, but try to describe this omega-2 as explicitly as possible.
Okay.
Because I don't think that everyone will be comfortable with this notation.
Okay, so recall that this is just projection, the 0, the other projection. Okay, recall the V1 is the multiplication. Right. So these are the three phase maps from G2 to G.
So the theta L, that one is.
Theta L and theta R are the left and right invariant Maurer-Cartan forms. It is nice, the story of this two-shifted symplectic structure. I think it first appeared in a paper by Weinstein, which is called the symplectic structure on moduli space. Although I think he says that they really first appeared in a paper by Jael Carchon, but at least in this particular way, he made them explicit.
So, for example, in the traditional notation, they write theta L as G inverse DG.
Mhm.
You know, so if we wrote it out, let's say that the coordinates on G cross G.
Yeah, let's call it EYU. Okay. So this is just the usual notation. Okay. Does it make sense? Check that this is closed with respect to the Bott-Schulman differential, right? Explicitly, this means that it is 0. Okay. That's what it means. Okay, but the important fact is that this two form is, so this means that the two form is closed. But it is non-degenerate, but as a two-shifted symplectic form. So remember what is, so we have to consider the tangent complex of our Lie group, right? We have zeros and we have the Lie algebra, right? I think that this lives on degrees 1 and this is on degree 0, right? And its dual lives here, right? So 0, G star, right? So the shifted cotangent given by shifting this guy by 2, right? So there is going to be a map from G to G star that is actually going to be, well, it has to be a quasi-isomorphism. It has to be an isomorphism. And this map is given like this.
So you're saying that in order for this to be a symplectic form, now that we know that it's closed, we just need to check that it's non-degenerate, and therefore we need to check that this 2 form induces an isomorphism from G to G star to be -1. Yeah, from So how are we supposed to use this form to obtain a map on the tangent complex?
Well, that's the tricky part. If you remember, in the one shifted case, it was relatively simple, right? When we had a 2 form, use a different letter. On the space of arrows of a Lie group, and we have its Lie algebra, right? What we defined, it was a certain map from its Lie algebra to the cotangent of the base. Suppose that.
Excuse me, could someone turn the camera, please? Thank you. I think it's button 2 that will do the trick. Thanks.
So this map, in this case, was given like this. Was given, okay, we can contract the 2 form with an element in the Lie algebra, and we could pull back the 1 form that we obtained to the base. In the simplicial notation, this. Okay. Well, this is not the unit inclusion. Okay. So this was a map that we wanted in the one shifted case. But so if you notice, well, we are using a degeneracy map because and here we have only 1. But if we move higher, right, we have 2 degeneracy maps. So it's reasonable to expect that these 2 maps are going to play a role here. And I don't know if I have enough space. Well, I guess it should be enough. The idea is okay. We can use the phase map to push forward this element to G cross G, and use the other phase map, other degeneracy map to pull back. Right. And do this. Right. But, there is also another choice, right? This is basically the map we want. explicitly so if we apply this pairing to an element U, and we pair that element with an element with another element of G, right? In this case as well. The phase maps, the higher phase maps of a Lie group are given like this. We take a string of composable arrows and we put a unit at the corresponding position. Okay, those are the degeneracy maps. Okay. And if we go back to the definition, we can see that, okay, this is going to be given by.
Sorry, so this second line, you're just rewriting what you wrote just above.
Which line? This line?
Yeah, you're just rewriting.
Yes, I'm just rewriting, yes. Mm-hmm. We can see that this is the pairing. So since the pairing is supposed to be given by a by a non-degenerate bilinear form, this is an isomorphism.
So here, when you evaluate omega-2 on U0, U0V, right? You're thinking of those as being tangent vectors to G, to the group. But the tangent bundle of the group, you're using what you're using left and right translations to trivialize it, and you're now viewing U and V. Yeah, so maybe explain a little bit more. Like, what is this omega-2? At what point of G are you evaluating this?
This is at the point. Yeah, the point one, right? Omega-2 lives on omega, lives here. So we are computing the value of omega-2 at 1, 1.
At the identity.
At the identity.
Identity. So in a way, okay. So in the case where you're looking at one shifted, the tangent complex was described in terms of the Lie algebra A, which is defined on X. And so when you take an element U in the tangent complex, that's a section of A, and you're lifting it to G, thinking of it as a left or right varying. But then you're just looking at its value on the identity bisection formula.
Yes.
Now in this case, there is no, the base is a point. So the tangent complex, you're saying that it's a copy of the Lie algebra in degree -1, and you're viewing that as as what? As a vector tangent to G. So you don't need to do any lifting in that case.
Yes, it is.
Like maybe, I don't know, I've always found, I mean, what you're describing is exactly how it's described in the literature, but there's something very annoying about it, which is the following, that if you have a simplicial space, which has x0, x1, x2, and all that, right? The tangent complex is only defined on x0. The tangent complex is defined on the base. Okay. And the tangent complex is just a way of approaching. It's a way of describing the tangent bundle of the stack, right? The most natural way to describe the tangent bundle of the stack would be to take the tangent bundle of the entire simplicial.
Yes,
Right?
for sure.
And then you have these forms which are defined on there, and then you could understand how tangent vectors on x0, x1, x2, how they pair with forms. But we don't do that. We have to do acrobatics.
Yes.
To take the form that's defined on the simplicial manifold, and we need to evaluate it on a vector which is defined in the tangent complex, right? And that's what makes everything complicated.
Yes. Yeah, I mean, this is kind of weird, right? I don't know if I mentioned that in the one shift case. So let's continue. So suppose that suppose that we had also a three form on the base, such that omega and H form a one shift symplectic structure. Okay. I mean, as you know, this H plays no role in the non-degeneracy, right? But anyway, so using omega, right, we can define a contraction map. Now on the tangent bundle of the Lie groupoid, right?
So omega flat, or is that?
Yeah, yeah.
Super B, or
Isn't that the usual notation?
flat? That's what you mean?
Yes, yeah, flat.
Everyone gets it.
Yeah. Right, we have the contraction map from the,
Put together what you just said. Actually, I thought it was sharp, but anyway, it's fine.
oh yeah, sharp is the other way, right?
I thought this one's sharp and the other one's flat.
Okay, so here we have this map, right? And the thing is that, well, okay, so this is clearly a Lie groupoid again, right? Because applying the tangent functor to all these structure maps here preserves everything, and so this is a groupoid.
Yeah.
And this is also groupoid, although not obviously. So in the cases of a groupoid, right? So these are both groupoids. And the non-degeneracy condition of this two form, instead of being described by infinitesimally like this, can also be described by saying that, okay, omega is non-degenerate if this map is a weak equivalence or a Morit equivalence. Weak equivalence. I mean, this computation appears in a paper by the lawyer. Well, this. Okay. So this definition is more satisfying, right? Instead of defining this weird object, it is more natural. Okay, you have a two form. Let's use the two form that was given to us, right? And express the non-degeneracy for that two form, right? But the problem here is that, okay, if we want to play the same game here, right? For the two shifted case, that is more difficult. Yeah, I mean, as far as I know, there is no two shifted cotangent groupoid. if that makes sense. Right.
Can you say a little bit more, just not to explain more deeply, but just repeat, what are you saying in this case is different?
Yeah, I mean, what I'm saying is that, okay, if we, okay, let's apply the tangent contour, okay? We get a simplicial manifold, okay? But now suppose that, okay, well, maybe we want to study what should the cotangent of a simplicial manifold be, right? That thing is complicated, right? Even for the case of a groupoid, right? Okay, it is very natural to consider, okay, let's dualize the tangent here, right? But in the two-shifted case, we would like to express the non-degeneracy here. So we would like to have somehow to study this guy, to put this cotangent inside some groupoid, right? Or simplicial manifold, right? That's what we would like. But that hasn't been described
But in the case
by anyone.
where this is the mirror of a groupoid, then we do have that. We have the cotangent groupoid.
Yes, but at the level 2, this is not what we want.
What is the cotangent groupoid at level 2?
It's going to be a fiber product of this guy over the dual of the algebra.
So you're saying that even if we were working on a groupoid like here, it's a group. And if you take the mirror of the group, and you take its, and you take the tangent bundle, that's a simplicial manifold. But if you take the cotangent bundle, it'll become a co-simplicial manifold, and that's that we don't like to use that for some reason.
Yeah, I mean, things I don't even know what would the phase maps would be in this case. If we dualize that. So I think that's one of that's the reason why people always move on to this infinitesimal picture. Anyway.
So there's a problem in the, you could phrase it as a problem and say that there's a lack of understanding of the cotangent.
Yes,
of the simplicial manifold.
I think so.
But you have a complete understanding of the infinitesimal way of accessing it. Well, that's a lot of data, that's a lot of information that could be used to maybe solve this problem.
Yeah, I guess so. I think Cheng Chang-Ju and the group were trying to study that kind of problem. But so far, I don't know if there are any results. Let me remember what. Okay. Oh, yes. So now let's move on to two-shifted Lagrangians. So the philosophy is like this: okay, we have a Lie group point of G, and we have a Lie group point morphism. Right. And well, a two-shifted Lagrangian structure, well, is going to give us in a sense a trivialization of the pullback of the two-shifted symplectic form here, okay, which satisfies some non-degeneracy property. So first, remember that an isotropic structure phi is just a one-shifted two form, one-shifted two form, yes. That is a primitive for the pullback of the two-shifted symplectic form in G. Let me just avoid the use of subindices. It's just to pull back. Let me just make explicit where these forms live. Here we have one shifted, two forms live here, right? And what we are saying is that, well, if we consider the corresponding Bott-Schulman complex of L. Let me put it here. I consider the Bott-Schulman of L, right? We have the pullback of this thing. And what we were saying is that, okay, there is a one shifted two form that trivializes this guy. Okay. Remember that here we have the simplicial differential, the RAM. Simplicial, okay.
There's one more element missing. The pullback vanishes at the bottom of this.
Yes. Let me continue. Maybe here.
This file, the map,
Uh-huh.
how should I, so is that literally a map from L1 to G? Like a groupoid homomorphism?
Yes.
Okay.
And I'm abusing the notation and I'm denoting its extension to the nerve by phi again.
By the way, just as a aside, it's conceivable that the map from L to G could be a zigzag. Right?
Of course.
But here we're simplifying and saying.
Yeah. We're simplifying things. Yeah, because also instead of G, we could take another groupoid that represents G.
Another what?
Groupoid that represents the same stack. But yeah, I mean, let's keep it that way.
This is like use of charts, right? So we're going to see certain Lagrangians in this chart.
And
maybe miss some others.
Do we have to worry about the symplectic shift? Like, how do I know that
when
representatives of the same stack are going to have?
Yeah, what happens is that whenever you have a Morita equivalence, that Morita equivalence induces a quasi-isomorphism between the tangent complexes.
Oh, right.
So it preserves what we are caring about, which is the degeneracy at the homology level of the tangent complex.
Indeed, that's the reason why shifted symplectic structures is a thing. That's why it's a real subject.
Right.
It's a stack.
You need like more restricted representations, like more refined everyday equivalence. Respects and
somehow the idea is that, yeah, different groupoid representatives of the stack, if one of them is shifted symplectic, they all are.
Yeah, maybe that's something that you should have mentioned at some point. But yeah, the cohomology of the Bott-Schulman complex is invariant under Morita equivalence. A good reference for that is, I don't know, a paper by Berendt. I think it is called cohomology of stacks. There he proves Morris invariance.
I went over these proofs in my class on shifted symplectic.
Okay, well, let's go back to the Lagrangian condition. So now we have a Lie group over here. So we have to consider its tangent complex. Right. And we're pulling back this two-shifted symplectic form. So it is going to induce morphism from this guy to the two-shifted tangent complex of this guy. Right, what the result is. And this is the map induced by. Okay. But now we have a trivialization of this pullback. And this trivialization induces a homotopy of this map to 0. So now this is, well, let's call it mu beta, perhaps. Okay. Implicitly, this means that if we take two elements here, this is just going to be the pairing of the Lie algebra applied to the images of these elements under phi, called d phi. And now we have the homotopy. Notation. That gives us this equation. This is what this condition means. So, well, for those who are familiar with Courant algebra, this looks like an isotropic condition in the sense of a metric, of a vector bound. Okay, so this means that we have a certain vector bundle over L0, which is L star L plus G 0, right? And what this condition means is that the map defined by the anchor mu beta phi Hence this Lie algebra here as an isotropic subbundle. Isotropic image with respect to the canonical pairing defined by the pairing between TL and T star, and minus the pairing on G, correct?
What's G all not?
The
The algebra later.
the trivial G cross L0.
Oh. So G, the Lie algebra. There's an action of the Lie algebra on L0.
No. In general, no.
So that's the trivial action algebra.
Yeah, we can think of
algebra on
it
L0.
that way. Mhm. But in some interesting situations, there could be an action of G. I have that much time left.
So actually, from the point of view of Courant algebra, you would say that G is an input over a point,
Mhm.
and that point has a non-trivial Courant algebra over it, which is just the Lie algebra across the point.
Mhm.
And then if you pull back that Lie algebra, if you pull back the Courant algebra to L0, you would get this one, this big one. And so
Yeah.
you're saying that the condition of being. Could you phrase it in terms of Courant algebra? So you're saying that in order for this phi to be a Lagrangian.
Yeah, an isotropic structure. Yeah, the isotropic condition simply means that this Lie algebra sits inside this object, which is a pullback Courant algebra, as an isotropic subbundle. Okay. The image of this bundle here is isotropic. The Lagrangian condition, as you might expect,
But in the isotropic structure, you have that this equation must hold. V of beta 1 plus beta 0 is phi star omega. So that integrability condition. Would you?
yeah,
Also included here.
not yet. Okay, maybe it is best to discuss that in the isotropic case. So this equation we can see this from the diagram, right? So since there's nothing here, this means that the d of beta 0 is 0. This means, well, that we have a closed tree form on the base of L. And we can, I don't know if all of you are familiar with this, but when we have a closed tree form on a manifold, we can use it to define as, well, twisted current algebra. Just current algebra, perhaps. Okay. Now there is another equation here. So what this equation implies is that this map here reserves bracket. I mean, this we know that preserves brackets because it is the anchor, and this is a Lie algebraic morphism. So what this condition means is something for this map. Okay. So the image is an isotropic involutive, a bundle of that thing. And if they fail to be smooth, but
What about the last condition, delta beta 1? Is it still negative 2?
yeah, there's a nice interpretation of this equation as well. Well, I mean, in a sense, this equation is what implies that we have this homotopy. So this, yeah, this equation is what guarantees this. Let's call this. This equation is what implies that. The homotopy property.
Is it saying that is it saying that there's a B field transformation between two?
Yes, in a sense, yes.
Beta 1 is what is beta 1? It's a two form on L0.
L1.
It's a two form on L1.
Mhm.
Okay.
Yeah, this is another story that maybe I'll just say it. So you can ask, well, okay, so if we have a closed two-shifted two form, what it represents, okay? For instance, if we have a closed two form, we can use it to define an extension of of the tangent bond. That's
Take some space, say that you don't say.
So we have a closed two form. We can use it to define a bracket here. Right, so in a sense, it allows us to define a Lie algebra extension of the tangent by R. That bracket being I don't know how to call this. Plus contraction. Right. So the fact that this two form is closed implies that this is a Lie algebra bracket. Okay. If we play the same game now with instead of two form, a three form, what we get is instead of a Lie algebra extension of Tm, we get a current algebra extension, right? So this is basically the Cervera's classification of exact current algebra. Okay, so in the shifted case, well, you can ask, well, what happens then, right? So, for instance, in this case of the Lie group, you have a closed three form on G, right? So we are in this position, right, of the current algebra extension. Let me just have a problem with.
Let's use the next.
So in this case, in this specific case, well, we have omega 1 and omega 2, right? So this leads to a current algebra extension. Okay. So what, and you can ask, okay, but this omega 1 doesn't come alone, right? It comes with a friend, that friend being omega 2, right? And you can ask, well, what's omega 2 doing here, right? So as we mentioned, this is a Lie group Poisson. Lie group actually. Okay. And the dual is also Lie group Poisson. Now over G star. This means that the sum Lie group Poisson. Given by the sum of these grouped structures. And what omega 2 does is that it deforms this grouped structure. So this is the canonical one, just the direct sum. Twists, perhaps. I don't know what's the best word. Okay. And this is something general. Whenever we have a closed two-shifted two form, we can use it to over a Lie group, or we can use it to consider this a twisted grouped structure on this direct sum. Okay, so what gives a remark? I said classify multiplicative current algebra exact, multiplicative exact current algebras over Lie group words. And how does that work exactly? Okay, the graph of the multiplication of this guy lives over G cross G. So the thing is that we can use this omega 2 as a B field. So we form the graph of the multiplication, of the canonical multiplication, to define a new one. The fact that this omega 2 is implicitly closed implies that this applying this B field transformation to the graph of the multiplication gives you a new multiplication. So it basically
Just say it again. So you're saying that the graph of the multiplication of this group word is in, where is it in? It's in 2G cross 2G cross 2G.
yeah, it lives over G. Well, it is best to think of it like this. We can see the product, right? G cross G cross G. And we can see the product of 3 copies of this guy. So the graph of the multiplication lives of the graph of the multiplication inside it. Here we have graph M. Here we have 3 copies of this guy. And here we have the graph of the multiplication of these groups. Let's call it M. And basically what happens is that omega 2 allows us to twist or acts on this graph as a B field.
But it doesn't affect the graph, the original application.
Oh. No,
It affects only the graph of the multiplication
Mhm.
tangent plus cotangent group.
Well, obviously, inverted like on.
yes. Anyway, this was like digression. If the image of this thing gives you a Dirac structure, can you see? This so this is a current algebra being the sum of this guy twisted by 0 plus current algebra with trivial angle by G 0. So examples, right? Let's. So this observation is what allows us to, well, to get a. I don't. I mean, at some point in the literature, it was asked, what is the integration of a Dirac structure that lives in a current algebra like this? Okay. So this concept of the shifted Lagrangian structure allows us to give an answer to that, right? And so based on this observation, we can say, okay, it is to be expected that if we have a Dirac structure here, and it is integrable, it should integrate to shift the Lagrangian structure on some liquid polymorphism. Okay. Let me just. Examples. For instance, you have a Lisa group of G, right? G is always a Lie group equipped with a metric and it's the algebra, such that H Lagrangian subalgebra. Then H is a Lagrangian has a Lagrangian structure given by 0, like this. There's two forms, 0, as I said, the shift Lagrangian structure. Now the extreme family of examples is given by a trivial group. Since we are saying that infinitesimally the shift Lagrangian structure is a Dirac, and decide that the current algebra of this kind. So if this guy doesn't exist, and if we have just an ordinary Dirac structure here, well, we can say that we have a two-shift Lagrangian in a point. So one shift is symplectic groupoids. Is the trivial group. Um, a less trivial example is given by this was important, but this example might appear a bit arbitrary, but you can see G cross G flipped with with the product of the two shifted symplectic structures and changing the sign in one of the copies. Another groupoid that we are going to consider is the following. We can consider the action groupoid associated to the left and right actions of G on itself. So we have two copies of G acting on G. One copy acts on the left and one copy acts on the right. And we have a morphism. Right. This group with morphism is just given by the projection. This action group is respect to left and right multiplication. And the two shifted symplectic, two shifted Lagrangian structure is, well, it's a bit complicated. So on the base, we have again the Cartan free form. And over here, we have a weird formula. Basically, we have two projections from this guy to G cross G. And we are going to use those two projections to pull back the two forms here. Okay. Namely, this one. This structure happens to be to shift the Lagrange. Example. Okay, but I mean, what's the point of all this discussion, right? There has to be a main theorem somewhere, right?
Are you done with this example, or can I say more about it?
Well, okay, you can say something.
Okay, so right-hand side, G cross G, you're taking the structure above on the top row there, and you're just doubling it, right?
Yes.
So you have a symplectic space, shifted symplectic space, and you're taking the predicate itself and switching the sign on that. So we normally think of the diagonal
Yes.
as being the Lagrangian
Yes.
side.
Yes.
side
Yes.
of this, right? So this is like the diagonal.
Yes. This is like the diagonal.
It's just that the thing that's being embedded in, what you really want it to be is the same thing as G itself. But instead, what you're doing is you're representing it in a different way.
With another group point. Yes.
With a different group point. So instead of thinking of it as G over a point, you're thinking of it as G plus G plus G over G, which is basically G is acting on the left and the right. So if you quotient out by the right action, that produces a point. And then there's a residual action of G on that point. And that's exactly what. This is really the diagonal.
Yes. So this funny group point is really Morita equivalent to G itself. And we are thinking of it as a replacement for the diagonal. The problem is that, okay, what we really want is to consider fiber products of two-shifted Lagrange. And this thing has the nice property of that this map is a submersion, right? So we can use this phi to consider fiber products of this with anything, right? Whereas the diagonal, well, it is unfortunately just an immersed submanifold, so we cannot really use it to produce arbitrary fiber products. So this is why we are considering this guy. Okay. In a sense, yes. You have the isotropy inclusion for every point. And so this is transitive, and we could consider any isotropy inclusion is basically a Morita equivalent.
So what Poisson just suggested is probably a good idea, that if you want to make it completely clear, you should have another G and make a zigzag. Right, so this G3 to G thing, that has a map to G over a point.
Let's call this, let's note this guy like this. And
Just erase the description of it as an attribute. That has a map to G over a point.
I think, I mean,
No, it should be the other way. The zigzag from G.
so you want another map? Okay.
Yeah, because you want it.
Yeah.
You want it to be that's G over a point. And The G gets mapped to a point, and
This thing maps here. Diagonal.
that's the generalized map.
Uh-huh. Okay. Yeah, I think in this case we can produce a quotient map from this guy to G.
That's right. So if you were to split,
Uh-huh.
if you were to choose a splitting, then you would get the bottom. But the point is that in terms of surjective submersion morphisms, it's a zigzag that does G into B plus G. So the composite arrow, right? You shouldn't really draw it. I mean, it's not a real arrow. It's not a real morphism
Yeah, this.
in the category of symplectic. It's not submerging. So it's not a covering one. If the other mounts there, they're looking at horizontal. Those are covering ones.
A very particular version of a super general theorem is that if we take psi, we have two shifted Lagrangians. Transverse, ensure smoothness. And this fiber product. One shift is symplectic. Here we have a Lagrangian structure. And here we have another one. And here we take, well, the pullback of both of them and we change the sign. So this is beta with a subindex. Fine. So this innocent looking result has a number of consequences. Well, let's call this example again.
P1 star minus P2 star.
Yes, of course. And here's the reason why we consider this guy. So we can take, for example, the fiber product of that guy with the actual diagonal. See it again. Okay, suppose that A and B are Lagrangian subalgebras.
So maybe it's worth saying a little bit about that thing about so. You could imagine that you start by taking the diagonal in G cross G bar and taking the intersection in itself. You start by saying, I want diagonal intercept diagonal inside G cross G bar. Why would you do that? It's because that's like it's like you're looking at loops, right?
Yes.
Inside the loop of G.
Yeah, this grouplet can be described as the grouplet of morphisms from Z to G, basically. So G can be identified with the morphisms from Z to G. Oh, okay, so now we can consider this as a space of objects of another grouplet. And that, so the morphisms between morphisms, natural isomorphisms. Morphisms. These are the arrows. Okay, but since we are talking about morphisms between two groups, this just means that this space is nothing but G cross G itself, right? It is as if we have a loop, a natural transformation. Yeah, I guess that's the reason why we can say that this guy is the space of loops in G. I don't know if that makes sense.
Oh, sorry. So is it correct to say that the AMM report is the isotropy in trying to get an understanding of we're looking at the diagonal inside G cross G. You can do this for any space, right? You take the diagonal of X cross X and take the intersection of the diagonal itself.
Mhm.
And that is supposed to be like that, but basically the point is that that is not, it's not a transverse intersection. So you replace this diagonal with GI, you compute the intersection, and then you get this ANMG.
Mhm.
Maybe it would be helpful to draw the picture that you usually draw with surfaces, but that's what you did, right? So you're
Yes.
saying that. Yeah, maybe try to explain a little bit more about the surface picture.
Yeah. Okay, you can imagine. Okay, so another description of this group could be like this. Okay, we can consider this. Okay, so this is a bit abstract. Let me just. Another description of the AMM group with. You can see that you have a cylinder, right? With one marked point on each boundary component. Okay. Sigma is this thing with 2 mark points. Let's call this sigma V, where V is the set that consists of these vertices. Okay. So you can consider, okay, let's consider homomorphisms from phi1, sigma V, the fundamental group width of sigma is V as its set of base points into G. Right, so here we have source and target, which are restriction maps. You can restrict a morphism, which of its of the boundary components. There's a nice way to visualize the multiplication. So you can imagine that you have 2 representations, right? By choosing generators of the fundamental group width, surface, well, you just need this edge and one boundary component. Okay. So we can represent a representation just with this picture, okay, by labeling this as A and B. So if we have another representation that agrees with this original representation along these boundary components, we can produce a new one, right? Which is just by gluing B prime, B prime. So this is multiplication. Rho and rho prime. Another way to say this, okay, so these morphisms we can view them as flat G bundles of the cylinder with a framing over D, right? And what we are saying is that, okay, if we have 2 flat bundles of the cylinder that coincide on one boundary component, we can glue them, produce a new one, and that gives us a multiplication. So we have subgroups of G such that the Lie algebras are Lagrangian. Okay, we have this thing again. This map of this inclusion. Okay. So again, the theorem says that this is one shift symplectic. Here something interesting happens. Okay. Guess I shouldn't erase that. So let's continue discussing that example. So what happens if these things generate everything, right? In that case, G together with A and B is what is called a Manning triple. And we have this thing, right? Okay. But instead of taking this, the fiber product of GI with A cross B, we're going to take the fiber product of GI with just 2 copies of A. Okay. We have this thing. And on the other hand, we have the inclusion of B and G. Let's call this JB perhaps. Now there's an operation of groupoids which is called the pullback. We can pull back this groupoids to a groupoid over B using this map. Basically, this condition guarantees that this pullback is going to be smooth as again. Let me just introduce notation, otherwise, so the sigma. So the miracle that happens is that, okay, so this thing is going to be one shift symplectic again. But not only that, this thing is going to be a symplectic groupoid. More convenient to describe this space like this. The elements. This is an example that I already mentioned, I think. This can be identified with this. So this is a symplectic. So the claim is that this is a symplectic groupoid, which is also known. It was found by Liu and Weinstein. Okay, and so symplectic groupoids correspond to Poisson structures. Okay, so this thing integration whenever we have a Manning triple, we have integrations, but leaving the double like this, we have what is called a Poisson structure on A and a Poisson structure on B, such that the multiplication maps are Poisson. So this induces what is called Poisson Lie group structures. Okay. So this symplectic group integrates one of them and actually integrates the other as well. And okay, so so if we change the roles of B and A in this diagram, right? What we can observe is that we get the same space here in the end. So magically, we get something, a symplectic manifold that has two groupoid structures, one over B and one over A, and these two groupoid structures are a symplectic groupoid structure. So
taking the intersection of these two shifted Lagranges, and I should get a one shifted symplectic.
yes.
Now you're rewriting it in a different way. Same thing, same space, right?
Not really, because this is now something different. This is a pullback along this map. I'm changing the base of the groupoid. In a sense, I'm restricting this guy to this.
Oh, so take the one shifted symplectic. That's on the right.
Yes.
And now you're intersecting it again with
this map. Well, this is not. This is not.
With the two shifted Lagrange. Or no.
Not really. It is like a restriction. We are restricting this guy to B.
Yeah.
That's what this guy is. So what happens is that this restriction, because of the transversality condition imposed by this equation, this is one shifted symplectic again, but yeah, but not only that, but it is actually symplectic.
But in order to go from being one shifted symplectic to being an actual symplectic groupoid, we simply need like a Lagrangian structure on the map,
Yes.
right? So that would be the map from B into this. So in order to see that there is a one, in order to see that there is a one Lagrangian map from B, should we use the fact that B was originally a two Lagrangian in G? And we see that.
Yeah, I think so. Yeah, because the original plan was to use this as a motivation for something else. Okay, so but I should just stop here. So this, yeah. So there's a way of. So notice the following. So A and B were two shifted Lagrangians in G. But thanks to this trick, we are converting A and B in genuine Lagrangians of manifolds of some symplectic space, which is this. So this is a general trick. Whenever we have well, certain condition, whenever we have two shifted Lagrangians in G, such that the associated Dirac structures form are in duality with respect to the current algebroid, we can produce the same kind of structure here. I don't know if that. So this is let me just erase. It was usually called. I don't know if that's going to clarify things right now. Suppose that we have two groupoids of the same base and morphisms G equipped with two shifted Lagrangian structures. In this situation, by the Lagrangian condition, we know that there is a map. Maybe 1, 5. So we have two Dirac structures on the same current algebra. We have this one, and the other one. So let's call these maybe A and B. So if it happens that, well, A and B are in duality, they are, meaning that they generate everything. So this is what people call a Lipay algebroid. In this case, we can play the same trick or a similar trick to the one that we used here in the Lug-Weinstein situation. And we can produce some type of space, let's call it D, in which L1 and L2 live as Lagrangian manifold. So we can produce a symplectic space in which L1 and L2 live as actual Lagrangians. And this D has a grouped structure, one over L1 and 1 over L2 that are compatible. There is a symplectic space D in which L1 and L2 live as Lagrangians. this space is equipped with two grouped structures, 1 over L1 and 1 over L2, that are compatible in some sense, that generalizes this situation. So yeah, the key fact seems to be this one, that we have two shifted Lagrangian structures that with this condition, with this duality. So this seems to be the key fact behind the Lou-Weinstein structure.
So what else were you planning? What were you thinking of doing?
Well, that was basically the end. Yeah.
Okay, thank you. If anyone has questions, please go ahead.
What's the form? Like,
Sorry,
I didn't hear it.
corn.
core? The core.
You're asking what is the core? Okay.
It is a fiber product. IMC. In this case, well, the core is trivial. In the Lou-Weinstein case. Or well, or it's good. The core would be the actual intersection between A and B, which is a discrete space.
The ANN group wave, that's supposed to be, I mean, they didn't think that it's a group wave when they wrote their paper. They were thinking of it as the modular space or quasi-Hamiltonian space associated to what? To,
Pair of bands. Yeah, I think it's a pair of bands.
this is the G action equal and itself by conjugation. Right? So that's supposed to be the connections on a loop with a marked point. So we think that so if you had a path with two marked points of boundary, and if you were looking for the modular stack of that. So let's start with like when you write G, okay, in these pictures, it's really, in a way, it's really VG, it's point mod G, like that's the stuff, right? So, now, what if you wanted, so this point mod G, right, it's supposed to be the classifying space for these bundles, G bundles. But if you,
Yeah.
use just like this GI, I'm just.
Yeah.
you're calling it
Yeah.
GI for a reason, right?
Uh-huh.
So why are you calling it GI?
Yeah, I mean that's correct. I mean, we can think of GI as the. I mean, there are several ways. Yeah, we can think of GI as the flat G bundles over the interval, right? The trivialization of the boundary, right? So this action, so this weird action is basically the residual gauge action at the boundary. That's what GI is supposed to represent. So that's why when we take the intersection with the diagonal, we close, right? We close into.
So the ANN groupoid is like the loop space of VG.
Mhm.
So in a way, you're thinking of maps from, when you draw a picture like an interval with two endpoints, right, we should think of mapping that into VG in a groupoid theoretic way, in the sense that we should have fundamental groupoid
Yes,
of the
exactly.
interval
Mhm.
mapping to the VG groupoid. In other words, when I say VG, I just mean the G groupoid of the.
Yes.
Right? So when you consider those maps, you would get the moduli space of
Yes, exactly.
connections
Mhm.
with frames at those two boundaries.
Yes. Mhm.
And so,
Yeah, that's why I put this notation of I1 as one. We're replacing the circle with this implicit model given by its fundamental group itself. And the nice thing that, well, this works as well for compact surfaces of positive genus, right? Because they are also Eilenberg-MacLane spaces, and we can represent them basically by their fundamental groups, right? But if we wanted to play this game for higher dimensions, we need some much more complicated object instead of the fundamental group or group, right? So this game can only be made explicit basically at this level, the dimension from 1 to 2.
let's leave it there. Thank you again. Next week. Álvarez, do you recall what it is?
Sorry, I can